Hi everyone, today we're going to cover topic 5.4, elementary reactions. So we've learned before that reactions can occur all at once or they can occur in several discrete steps. The way that reactions occur we define as a reaction mechanism, which is essentially the pathway a reaction takes. If it's in multiple steps, each step is called an elementary reaction. So each step of a reaction would be known as an elementary reaction or sometimes an elementary process. And so an example of this is the conversion of O3 to O2. And so this actually occurs in two discrete steps, and so it has two elementary steps. The first is that O3 gas reacts to form O2 gas plus just a free oxygen. The second step is that O3 gas plus oxygen, that lone oxygen we got from the first step, react together to form 2 moles of O2 gas. Now, we've seen this before with Hess's law, and that is if there's a common intermediate, you can add reactions to make an overall reaction. So in this case, our common intermediate is oxygen, or just oxygen on its own, not oxygen gas. You see they end up on opposite sides of the reaction and they have the same stoichiometry, so we can just add these two together to get an overall reaction of 2 moles of O3 gas react to form 3 moles of O2 gas. Now, of course, I can just give you this bottom reaction, but that doesn't give me enough details. That basically just says that 2 moles of O3 will react to form 3 moles of O2, but it doesn't say that in making that we have 2 steps where the first step generates an O. The second step uses that same O in order to form O2. And of course, because they're on opposite sides, they will cancel out. So you get this overall reaction made of 2 elementary steps. Now, another term that we typically use to describe a reaction is known as its molecularity, which is basically how many reactants are needed in the elementary step, or the elementary reaction. And so let's say we have this case where something called A goes to products. Doesn't matter whether or not the product is 1 thing, 2 things, 3 things, it goes to products. We call this a unimolecular reaction. Uni meaning 1 molecule. And we can describe the rate of this reaction as follows. The rate is equal to K, lowercase k, times the concentration of A. We can have another reaction where we have A plus A goes to products, or we can have A plus B goes to products. In both of these cases, we call this a bimolecular reaction. Bi meaning 2. It requires 2 reactants in order to form products. And the rate can be expressed as either K times concentration of A squared, that's the first case, or in the case of A plus B, the rate is equal to K times concentration of A times concentration of B. So for a bimolecular process, we'll have a rate constant that looks, or rate law that looks like that. Now, we don't often see this, but there are examples of it. And this is the case of 3 things reacting together. We can have A plus A plus A, we can have A plus B, or A plus B plus C. All of these, of course, go to some products. It does not matter how many products. All that matters is how many things start in your reaction. We call this a termolecular reaction. As you might imagine, the rate law looks pretty similar. We can have, for the first case, the rate is K times A cubed. For the second case, the rate is equal to K times A squared. A squared times B. And for the third one, rate is equal to lowercase k times A times B times C. And so generally, the rate law looks very similar to the type of molecularity that you have. One thing that I will say is that termolecular reactions are extremely rare. In other words, they basically don't really happen, and if you ever get an answer with a termolecular product or a termolecular reaction, something may have went wrong, because generally these are extremely rare and you don't really see them. Now, of course, if we have multiple different reactions leading to an overall reaction, clearly you're going to have to add their rates together or consider all their rates together in some way. Now, we must remember that the overall reaction cannot occur faster than the slowest reaction in its mechanism. That slowest reaction we call the rate determining step, because that's what actually determines the rate of your whole reaction. You can take this example below. Here, it says cars slow at the toll plaza A. So they're really slow here, and so you have a pileup right before this first toll. But then at toll B, you can say they're going much, much faster. So at A, they're going slow. At B, they're going fast. We can say that A is rate determining because that contributes the most to the overall rate of the reaction. In this second example, it's the opposite. In toll plaza A, they're moving quite quick, but in B, there's a pileup. In this case, toll B is our rate determining step because that is the one that contributes the most to the rate. So whichever rate is slowest is rate determining. So let's look at this one practice problem from AP Classroom. We have a two-step reaction. H2 plus ICl makes HI plus HCl. We call this the slow step. Slow is another word to say rate determining. So our slow step is rate determining. So that happens first, and then we have the second step, which happens really, really fast. We have HI, which we make in this first reaction, reacts with more ICl to make HCl and I2. So it's asking us which of the following represents the overall chemical equation for the reaction and the rate law for the elementary step 2. So we're interested in the rate law of this and the overall reaction. Now, previously when we were doing Hess's law problems, we'd have to flip a lot of reactions in order to cancel everything out. In this case, that's not really going to be possible. What we need to look for is just a common intermediate that shows up on the products of one reaction and the reactants of another. In this case, the common intermediate is HI. So all we need to do is just add these two reactions together in order to get a new reaction. And that will give us our overall. So if we have H2 plus ICl makes HI plus HCl, our second reaction is that same HI reacts with more ICl to make more HCl as well as I2. All we got to do is add these two reactions together. We can see that our H2 will come down to the bottom. We have ICl in both, so we get two ICLs. We have HI on the left and HI on the right, and so both of those will cancel, and we don't end up seeing that in our final overall reaction. We have two HCl's on our right side, and so we end up making two HCl's, and I apologize, I meant to put a 2 in front of ICl. And we make I2. And so overall, this would be our reaction. If we look down at all of these answer choices, answer choice A has just one HCl, and so this can't be that one. Answer choice B has it in correct form, H2 plus 2 ICl makes 2 HCl plus I2. So that one might be good. For the third one, part C, we have H2 plus ICl plus 1 HCl, so it can't be that one either since the stoichiometry doesn't fit. And for answer choice D, that one also fits in terms of the reaction as well. And so now we need to look at the rate law of reaction 2. And if we look at our answer choices here, they look pretty similar. For answer choice B, it says the rate is K times H2 times ICL squared. And for answer choice D, it's the step 2 is the rate is equal to K times HI times ICL. Now, the important thing to remember here is that stoichiometry does not go in the exponent. Remember, the exponent is equal to the reaction order. And this can only be determined experimentally by looking at rate changes. At rate changes versus concentration. And so it can't be this one because we have absolutely no indication that it's ICL squared. We have no indication that doubling the rate would quadruple the rate, or it would be the rate squared. And so our answer choice here would be D. We have the correct overall equation, and our rate law is satisfied as well. We'll do some more practice in class, but for now, that's all. Thanks, guys.